Hello everyone, today I am here to present our paper, Coordinated EV Aggregation Management, the Alternative Direction Method of Multipliers. This paper has been done with the contribution of my colleagues and my advisor at Connected Smart Group at the University of Tennessee. First, we are going to have an introduction over the topic. After that, we are going to check the distributed charging platform that we have used in this paper. In the next step, we are going to see some simulation data and results, and finally, conclusion. Okay, let's start with the introduction. The expansion of electric vehicle fleet in the last decade has been remarkable. It is expected that the global energy demand for EV will increase from 20 billion kilowatt-hours to about 280 billion kilowatt-hours in 2030. And this unprecedented growth of electric vehicles has the potential to avert a catastrophic impact on climate change, but the challenges of the EV integration cannot be overlooked. So here the role of electric vehicle aggregators is really important, so they can manage the electric vehicle charging. Charging management can be solved using centralized and decentralized methods. And despite the fact that centralized algorithms can guarantee performance, they have some issues such as privacy issues or complexity and so on that you can see in the next slides. This paper established a distributed optimization platform based on the alternative direction method of multipliers for optimal electric vehicle charging management, and we have used MIQP model to cover the charging and discharging constraints. The contribution of this paper is 3 points: to formulating the nonlinear EV coordination framework as an ADMM-based MIQP problem, creating a comprehensive model for the bus tree operation in optimization problem, including energy constraints and charging and discharging, and finally considering the symmetric charging and discharging price. So in the left side of the screen, you can see a centralized electric vehicle charging platform. So in that system, electric vehicles share all their information that is needed by the aggregator to solve the optimization for all of the agents which are electric vehicles here, and send the charging profile back to each EV. On the other hand, in the distributed platform, each EV solves its optimization by itself and send the aggregated EV charging platform, or it can be also individual, to aggregator, and aggregator sends just a signal to electric vehicles to just complete the loop. About the centralized and decentralized optimization for electric vehicles, here we have some comparison. For example, in terms of scalability, just imagine we have a pre-designed system and we are considering to add a new region which have a lot of electric vehicles. So in terms of scalability, decentralized methods do not need a lot of changes, but centralized, since all the optimization should be done by an aggregator, it has some changes. About the privacy, communication overhead, and computational complexity, also decentralized method shows the better showing the better performance compared to centralized methods. In terms of performance constraints, most of the constraints can be guaranteed in a centralized method, but in the decentralized method we still have some problems. So that's why we are working on this part in this paper. So about the distributed algorithms, they can be classified based on consensus theory and subgradient methods. Gradient-based algorithms are well-established distributed algorithms. But why we have used ADMM, or alternative direction method of multipliers, among all the distributed algorithms? ADMM is really popular because its capability to handle large-scale problems and to support non-strictly convex functions. Okay, let's go to the optimization problem. Here we use a general optimization platform, in which FA is showing the aggregator objective function, and FI is showing the agents or electric vehicles objective function, and gamma is the trade-off between these two. So basically, we can use this formula for any system which you have an aggregator and a lot of agents. XA is the power balance between aggregator and electric vehicles, and it's a global constraint which we need to consider here. As a case study, we set the objective function of, for the aggregator, we consider load variance minimization, LVM, charging cost minimization as the objective functions. And for the electric vehicle, we consider battery degradation costs, since it's really important in EV charging management problem. Okay, EV objective functions and constraints can be seen in this slide. So we use a quadratic objective function to model the battery degradation cost, and after that we model the energy balance, we model the power exchange and energy exchange. So as you can see in 2C, we decompose the problem to charging and discharging. So doing that, we can consider both charging and discharging problems, and in 2D you can see using some binary variables we just avoid to have charging and discharging at the same time when we are connected to the system. But considering these binary variables makes the problem converts the problem from a QP model to an MIQP model. It should be noted that because we use ADMM, the problem is always quadratic problem, because the augmented part of the ADMM that we show in the next slides. So EDA objective function and constraint can be seen in this figure, in this slide. So 3A is the load variance minimization, and 4A is the charging cost minimization. But still we have some binary variables here to just consider charging and discharging on negative or positive energy tariffs. So you can see how we decompose charging, the formulation, the power exchange to charging and discharging. Okay, problem decomposition can be here, which has been done based on the exchange problem that's suggested by recommended by Dr. Boyd. So you can check the reference here. He's the main guy who is using the distributed optimization, basically ADMM in power systems application. So ADMM-based approach has been introduced in this slide. So you can see we have the augmented part, we have the objective function, and we are updating the Lagrangian multiplier at each step. We also update the average charging of all electric vehicles on aggregator at each iteration. So you can see here. Actually, these two are the signals that aggregator sends to each agent to make the loop complete. So here you can see the objective function of electric vehicles, EV aggregator, and the update of Lagrangian multiplier. So using this, it's actually the same as the previous slide, considering each agent separately. After that, we are going to open the equations to this one. So you can see it has all the equations in this platform. About the convergence criteria, so here use primal and dual residual. Primary residual is actually the average power exchange, and we reach convergence, and we are when these two values be less than gamma, sigma actually. So at this slide you can see the whole platform. So the algorithm is working like that. First, all electric vehicles do their optimization for themselves. After that, the aggregator, and we update gamma and x average. And if we are not reaching convergence, we do the loop again using by updating xi and gamma and lambda. So let's go to the simulation data and results. So we use Southern California time of use for our data. For the demand data, we use Munich distribution system operator data, and for the electric vehicle data, we use CARTA or Chattanooga Area Regional Transportation Authority. So you can check it in the paper with more detail. About the simulation scenario, we use two scenarios. The first scenario is the impact of different value of gamma on the final demand profile, and the second one is the impact of considering new constraints using MIQP optimization. So about the gamma scenario, you can see we considering load variance minimization and charging cost minimization for both without V2G and V2G cases. So when gamma is equal to 1, that means we are considering all the agent's objective function with a really high trade-off value. So we are not getting a good result in terms of value filling and peak shaving. On the other hand, when we have gamma 0 or near to 0, so we are getting a better result. In case we have V2G, so you can see that the result is even better, so peak shaving and value filling is better. About the CCM charging cost minimization, the result is the same. So here, because we have a change in the price, actually the optimization tries to charge electric vehicles in the off-peak hours. About the second scenario, which is MIQP but QP method. So we have two cases. In case 2, which is a QP, we don't have those charging and discharging constraints. So you can see the results. It's really optimistic, so or not realistic even. So you can see when we have V2G, we almost have a flat curve during peak hours. On the other hand, in case 2, we don't have such a thing. About comparing V2G and without V2G, you can also do the same results as the previous case. Let's go to convergence analyze. Our method is converging, so you can see the primary residual and dual residual convergence with these two figures. And about the runtime analyze, runtime analyze in the MIQP model is much more, but 2 times actually more, but we are getting more information from this optimization. So conclusion, in this paper, an ADMM-based CD charging platform problem is formulated as an MIQP optimization problem, and we consider P2G, so these are P2G constraints, and symmetric charging constraints. In the future, we are focusing on fully distributed methods, as we have already done the same research on economic dispatch problem that you can see in this paper. Thank you for your attention.